All right, so as I've mentioned, calculus is made up of three parts: limits, derivatives, and integrals. So today we're going to start using limits to find derivatives. So our learning target is we want to be able to use the limit definition of the derivative of a function to find derivatives. So what a derivative can do is that it finds the slope of the tangent line to the curve at any point. Let's take a look back at our warm-up problem. This was our warm-up problem, and I asked you to find the average rate of change over 0 to pi over 4. We found this point to be 0, 4. We found the point at pi over 4, and when we plugged in pi over 4, we knew the sine of pi over 4 was radical 2 over 2 plus 4. So this was radical 2 over 2 plus 4. So we could find the average rate of change from here to here. But with calculus, what we want to do is find the rate of change just at one point. So up to now, we've had to have 2 points to find rate of change. But now we're going to talk about how we can find the rate of change at just 1 point. See, look. Between here and here, that's a pretty good estimate for the slope at pi over 4. But look what it actually is if I draw the tangent line. It's more like that, okay? Only with calculus can we find that slope of that tangent line and find what's called the instantaneous rate of change. And so here's what we do to find it. Rather than calling these specific points like that, I'm just going to talk in general. I'm going to call this point x, and then the y value would be f of x. Well, if I want to find the point right there, I can take another point that's pretty close to it, and I'm going to say that I've just moved over h units. So this point now is going to be x plus h. If I want to find the y value right here, I would have to plug in x plus h. So the y value would be f of x plus h. If I want to find the slope between these 2 points, what do I have to do? Use what formula? Slope formula, right? So to find the slope between these 2 points, I'd say the slope is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. What does the denominator simplify to? Just what? H. So here's my formula. But I don't want that h value to really even exist. If I want to find the slope just right here, what would I truly want that h value to be? How much do I want to move over? 0, right? Because I want that h value to be really this point right here. And that's where our limit definition comes from. Because I want to have the difference between these points to be 0, I have to create a limit problem. And this is where we start with derivatives. And that is the reason that we had to study limits. Is because if we want to find the derivative, we have to know how to find the limit. All right, so back over here now. Oops, not there. We are trying to find that slope of the tangent line to the curve at any one point. And I just said that's going to be called the derivative. These are common symbols that we use to represent the derivative. Differentiation is just the noun form. It's the process that we use to compute the derivative. So when I say find f prime of x, that means to find the derivative. dy dx, find the derivative. Y prime, d dx of f of x. All of those mean the same thing. They all mean find the derivative. Limit definition of the derivative. Here's one way we can write it. The derivative can be thought of as f of x plus delta x minus f of x over delta x. But what happens is we kind of get tired of writing this delta x. What do you think delta x means? change in x. And what do we want that change in x to be back here on my problem? What do I want that change in x to be? 0, okay? And so we say this is a great formula to use, but a lot of colleges have gone to calling it, instead of delta x, to h. It just, after you do a bunch of problems, you find that it gets a little annoying writing delta x over and over. H is a little bit easier to write. But these formulas are the same formulas. We're doing y minus y over the difference in the x's, and the difference in the x's, we want it to be 0. Alright, so we're going to start off by finding derivatives with respect to the appropriate variable for the following functions. So here's my function. I want to find f prime of x. So f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. So that means I'm going to write this limit. This means in my function, wherever I have an x, I have to replace that x with x plus h. So that's going to give me 5x plus h, put the x plus h in parentheses, minus 4. That's what this part would be. Look again, I'm writing the whole function, but I'm replacing the x with x plus h. Now I have to do minus f of x. Well, f of x was just this, all over h. Well, simplifying this now, I'm going to distribute. I have 5x plus 5h minus 4 minus 5x plus 4 all over h. Alright guys, what's going to happen here in the numerator? Yeah, a lot cancels, doesn't it? 5x minus 5x cancels, negative 4 plus 4 cancels, so now I'm just left with 5h over h. What's that going to be? 5. We just found our first derivative. F prime of x is just 5. Does anyone know why the derivative would be 5 based on what I've said? What did I say the derivative represents? The tangent line at any point. If I have the line 5x minus 4, it looks like this. The tangent line is always going to be the line itself. And what is the rate of change, or what's the slope of the line at any point? 5. If we're given a linear function, we don't have to do all that work to find the derivative, because the derivative is just the slope or the rate of change of the function at any given point. And so it's 5. Now, 2 over x. Before we start, let's think about what that looks like. That's going to be this reciprocal function, has a vertical stretch of 2, but it's going to look something like this. Not perfect, but good enough. Is that always going to have the same slope everywhere? No, not at all. So I'm going to have to use my limit definition. So, to find y prime, I have to do, in my function, wherever I have an x, well, first I have to write limit. In my function, wherever I have an x, I have to replace that x with x plus h, using the formula right here. I'm doing f of x plus h. They didn't call it f of x, but this is f of x. So this gets replaced with x plus h. Now I have to do minus f of x. What's f of x? Just the function, which is 2 over x, all over h. So now this is what I have to simplify. Do you guys remember what we did with limits when we had a complex fraction? Nathan, what do we do? You forget? Morgan? Good, she's right. The common denominator would be x times x plus h. So I'm going to multiply by that. X and x plus h on top. If I'm going to multiply the numerator by that, I also have to multiply the denominator by that. So now I'm going to simplify this, and this should get rid of my complex fractions. When I multiply this term, the x plus h's cancel, and I just have 2x. When I multiply this term, the x's cancel, so I just have negative 2 times x plus h. In the denominator, nothing cancels, and I never multiply out that denominator. It just makes the problem worse. Because my whole goal is to be able to get rid of this h on the bottom. See, way back here, if I plugged in 0 for h, I get 0 in the denominator, which I can't have. Same thing here. I'm going to get 0 in the denominator and 0 in the numerator, both times. When we get 0 over 0, we have to do more work, and that's why we're doing this more work. So now I've got 2x minus 2x minus 2h over hx times x plus h. My whole goal is to be able to plug in 0 for h, but I can't do it yet. 2x minus 2x, though, those cancel. So now I've got negative 2h over hx times x plus h. See, back here, I couldn't cancel the h's because it was terms, but now these are factors. Once it's factors, I'm allowed to cancel these h's. And so now I've got the limit as h approaches 0 of negative 2 over x times x plus h. Now I can plug in 0. If I plug in 0 for h, what's my answer going to be for this y prime? Negative 2 on the top. I plugged in 0 for h, and so I just have x times x, and what's that going to be? X squared. And so that's going to be our derivative. Okay. All right, we're going to do 2 more derivatives. Okay, example 3, d dx of g of x. That looks really complicated, but all it's saying to do is to find the derivative. All right, so to find the derivative, I'm going to call it g prime of x. That's going to be equal to the limit as h approaches 0. Wherever I have an x, I'm going to have to plug in x plus h. Then I have to cube it plus 2. That's what I get when I do my g of x plus h. Now I have to do minus g of x all over h. Does anyone know how x plus h cubed multiplies out? It's not just x cubed plus h cubed, unfortunately. You guys may have seen this on my board. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Have you guys seen that on my board from Honors Algebra 2? This is Pascal's triangle. What this does is it quickly tells me how I can cube this out. See, I can do x plus h times x plus h times x plus h, but it's really kind of a challenge to do that. It takes a long time. This tells me that whatever my first value is, it's going to be x cubed. Then it's going to go x squared. Then it's going to go x, and then I'm not going to have an x. With my second term, I'm not going to have an h. Then I am going to have an h. Then I'm going to have an h squared, and then I'm going to have an h cubed. So what this tells me, this 1, 3, 3, 1, it tells me the coefficients. So my first term is going to be 1x cubed. My next term is going to be 3x squared h. Just looking at this. My next term is going to be 3x h squared, and my last term is going to be h cubed. That's what I get if I were to multiply this out. Now, I'm going to do it the other way just very quickly. If I multiply this out, it's x squared plus 2xh plus h squared. Then I'd have to multiply it again. I'd get x cubed plus x squared h plus 2x squared h plus 2xh squared plus xh squared plus h cubed. And then I'd have to add all my like terms. Do you see how much longer that takes than understanding Pascal's triangle? So I now have that expanded, and I prefer to do it with Pascal's triangle. I could have done it by multiplying it out this way. I would combine my like terms, and I would get this. I would get the same exact thing. But it would just have taken a lot longer. Alright, so this part's done. Now I have my plus 2. Now I have my minus x cubed and my minus 2. All over h. If I have done this algebra correctly, then a lot of terms should go away when I subtract. So, these two, 0. These two, 0. Now I'm left with this term, and this term. What can I factor out of those? H. So now I've got the limit as h approaches 0. I'm going to factor out an h. I've got 3x squared plus 3x plus h squared, 3xh, all over h. So now these h's cancel. That's my whole goal, is to get rid of that h over h. That was causing 0 over 0. Once those are gone, I can now plug in 0 for h. That's going to be 0, that's going to be 0, so I'm going to have just 3x squared. That's all I have left. And so that's going to be my derivative. So what this derivative does is it now would allow me to find the slope at any point for this function. If I wanted to know the slope at 1, it would be 3. The slope at 2, it would be 12. The slope at 3 would be 27. See what I'm doing? Just plugging in those numbers now to find the slope. Alright guys, there's one more type that I'd like to show you, and that's finding the derivative when we have a square root function. Alright. So, here's my function. I'm trying to find y prime. It's going to be the limit as h approaches 0. Wherever I have an x, everything stays the same, but x has to get replaced with x plus h. Minus my function all over h. That's my setup. Again, look at what I did. F of x plus h is this, minus f of x over h. The sooner you can memorize this formula, the better off you're going to be. If you understand where it comes from, it's not that difficult. This is the second y after we move over h units minus the first y is our original function. And then h is just the difference in the x's. That's how far we moved over based on my original picture. So that's what I just keep using over and over. Right, does anyone remember how we handle this when we have the difference of two roots? Conjugate is correct. I'm not allowed to square it. If I square something, I change its value. For example, let's say a value is 1/2. If I square the top and bottom, what's it going to become? Is 1/4 the same as 1/2? No, I'm not allowed to do that. So I have to do something else instead. I have to multiply by the conjugate. The conjugate's going to be radical x plus h plus 1 plus radical x plus, or is it minus? No, plus 1. I have to multiply by that on top and bottom. So, in the numerator, if I multiply something by itself, all that happens is that radical goes away. So I just have x plus h plus 1. The whole reason we do conjugates is because the outers and the inners are the same, and one is positive and one is negative, so they're always going to cancel out. But here's where you have to be careful. When I do the last times the last, it's going to be minus this quantity of x plus 1. Can you see how people would probably forget to put those parentheses? I'll point that out because that's where you're going to miss this kind of problem. It's minus that quantity. The denominator, never multiply it out. It's just going to look ugly, and we'll have to just wait until the end to deal with it. All right, so now I'm going to just distribute through this negative. That's minus x minus 1. Just distribute it out. So now we've got x minus x, positive 1 minus 1. So what do we have left on the top then? Just what? H. So if I just have an H on the top and I have this H on the bottom, am I allowed to cancel them now? Yes, because I just have H. So now I'm allowed to divide. It's a factor now once everything else is gone. So at this point, I have a 1 on the top, and I've got this on the bottom. Almost finished with this, because now I can plug in 0. See, before now, I was going to get that 0 in the denominator. But now if I plug in 0, I put in a 0 here, I've got 1 over radical x plus 1 plus another radical x plus 1. So my derivative then is going to be 1 over, I have one of these plus another one of these, so I've got 2 of these radical x plus 1s. And that would be the derivative. Okay? Lots of algebra with this. The people that I know who are taking this calculus over at Miami, they said, you know, this was the most challenging part, just getting started with these limits, because there's so many places for errors. But these are the types of problems you're going to see in any Calc 1 class, this kind of rigor. All right, we're going to stop there.